So good morning again, and welcome to the second lecture of Memory Design and Test course. Today we will look at memory types and optimizations, and we will look at, hopefully we will also get to look at the design flow or the signal flow inside the memory, a typical signal flow inside the memory, and then subsequently, if time permits, we will also get to look at one of the data sheets so that we get a view of what kind of features are usually available inside a memory. So, but before we enter into all that, why do we need to talk of memories, and why all this hoo-ha in the first place? So the reality is that there is memory, some kind of memory, very widely spread out in the entire system. There are very fast registers and data paths. There are memories which are operating at processor speed, which are inside the processor. There are level 2 caches, level 3 caches, and then off-chip memories like DRAMs and hard disks. So memories are so pervasive in our electronics ecosystem that how they function, how to make use of them, how to design better memories, all this understanding can help us really leapfrog and transition into next level of PPA efficiency. PPA, all of you remember what is PPA?
Yes, sir.
What is
Power,
PPA?
performance area.
Yeah, power, performance, and area. For any VLSI system, these are the three parameters which a designer should always keep in sight. One should always have a sight of how is the performance of the system evolving, how is the area, which would result in cost of the system evolving, and how is the power changing. So all of us understand why all these three parameters are important. PPA, all three are important. Why? Hello?
Yes, sir.
Why is power important?
To reduce the losses like heated, if more power consumes, it will cost.
Yes, if more power consumes, there are multiple things. All of us are using mobile devices, portable devices. If our chips and if our systems consume more power, then we have to recharge our devices more often. Or to reduce that frequency, I have to use a bigger battery. Bigger battery means more system cost. Power also means whatever power is consumed also means heat dissipated. So if the power consumption is very high, then I also have to put in place sufficient mechanisms to dissipate that heat, to remove away that heat from the system level. So if you have very high power consuming system, you will have to have complex cooling mechanisms like liquid cooling. So in the last course, the DVD course, we also talked about how Qualcomm chips and the most advanced application processors actually tout about or claim good efficiency because they are using liquid cooling technology. So power is therefore very important. Performance, I think all of us very well understand. Why is performance important?
So we can say performance mainly includes functionality and the frequency of operation. So the functionality that we need should be as it is, and the frequency of operation, the desired frequency of operation at which the chip should operate. Yeah, that is also fixed.
So why is it important?
So
Why should we keep it in sight?
So performance ultimately boils down to the user experience. So if the higher is the performance, so we can operate the chips at a higher frequency and then get the results at a faster rate.
The throughput would be higher. The latency that the customer or a user experience will be lesser. So overall user experience improves. He or she is ready to pay a higher price. You are ready to pay a higher price for a higher performing Intel chipset, is it not? So performance also is important. That means that what kind of revenue we will earn. And area, why is area important? Oh, Vaishnav is saying area is gold in VLSI. Good.
To reduce the cost.
To reduce the cost. Why does area reduce the cost?
We get less chip area, so the silicon substrate is costly. So yeah.
Okay, if you have lesser chip area, then
If we reduce the area, then we can increase the lots of feature by adding some more transistors.
okay, we can do more integration. Yes. What else?
So the size of the devices also decreases actually.
So
we like
faster device latency will also decrease, sir. I think.
Interesting. So, sorry, Shivendra.
Sir, cost reduce.
Cost reduce. Yeah, that is what I'm asking. How does cost reduce when you reduce area? So Kazi said something. Kazi said if you have lesser area,
we can have more dies.
More dies on the same
more
wafer.
dies on the same wafer.
Because the cost of the wafer remains constant. If you can have more dies on the same wafer, you have more selling chips. Additionally, we also discussed and we also reviewed that yield is inversely proportional to area. So if the area is less, then what happens? Your yield improves. Yield improves means that if there were 90 out of 100 dies that were functional earlier, now 92 would be functional with a 2% improvement in yield. So not only do you get more chips per wafer, you get more functional chips per wafer. So overall profitability increases significantly. Therefore, we say that area is gold in VLSI. But for memories, we will say something else. What would we say?
So diamond.
Yes, for memories, area is diamond. Why? Because you see, memories are everywhere. In fact, in advanced SoCs, for the likes of the chips that are used in self-driving cars, for example, for advanced SoCs or for even advanced processors, up to 70% or even 80% of chip area is from memories. So if 80% of your chip area is memory, then to save area in memories is still more important. And that is why when we talk of memories, we say area is diamond. So we're changing the paradigm that area becomes all the much more important parameter when we talk of memories. Is that clear? Any questions? Okay, no questions. Now, while we saw that memories are used across the entire range of system hierarchy, we also need to understand that there are many different kinds of memories that we talk about or that we design. So the most common memory that we know of is SRAM. We talked about it even in the last part of the DVD course. Then we talk about DRAMs. DRAMs, all of you know. What is a DRAM? Where are DRAMs used?
DRAM is basically a single transistor based memory cell, which is backed up by a capacitor, which which dynamically stores the charge, which in fact stores a single bit of information.
Where are DRAMs used? Like I asked you, have you heard of DRAMs? And I'm sure you have.
DRAMs
so when you purchase your phone, what is the DRAM specification there?
The RAMs,
the main memory.
Where it says 8 GB RAM or 16 GB
RAM.
RAM, that actually is DRAM. Okay, and as you rightly said, DRAM is based on a one transistor cell, and due to this, it is much denser than an SRAM. For SRAM, we already saw in the previous class also, and we will see in much more detail in this class that SRAMs, the most commonly used cell is a 6 transistor cell. So 6 transistors mean some area, Whereas DRAM, if it is just one transistor and one capacitor, since it's just one transistor, it's denser. Okay, and with memories, area is diamond. So DRAMs are very important. Okay, so this is about the access pattern. They are random access memories. What does random access mean?
So we can write or read from any particular location at any particular time.
Yes, I will give an address and the memory, and I can read or write any location. So where are SRAMs? The DRAMs we already discussed. SRAMs would be typically used as caches, for example, or L1 cache, L2 cache, and so on, where you have an instruction which may carry an address and you want to write at that address. So this is about the DRAMs and SRAMs, but there are also non-random access memories that we have in our system. So FIFO, what does FIFO stand for?
First in, first out.
First in, first out. Where do you think a FIFO would be used in a system?
So when we are using a frequency conversion, like when we are using, like there is a change in frequency from one system to another, we are using them maybe.
Okay, good. So that is definitely one application of a FIFO, where we transition from one frequency island to another frequency island. Very good. Where else? So have all of you understood this concept? The frequency transition concept, have all of you understood?
No, sir.
No, sir.
No? Okay, so let us say that so all of us understand DVFS, and we in DVD also we talked about voltage islands. We said that depending on the system requirements, depending on the performance requirements from a particular system, I may operate some part of the chip at higher voltage, another part at a lower voltage. You remember this? We discussed all that.
Yes, sir.
Yes, yes.
So when we do that, when we operate system at different operational voltages, naturally the frequency at which those different voltage islands would operate would also be different. So there is one part of the chip which is operating at, let us say, 1 gigahertz, another part of the chip which is operating at 800 megahertz. Now, if there is some information transfer that has to happen from one part to the other, do you realize that there will be some extra data that could be coming from one side to be absorbed by the other side?
Yes, sir.
For that, we need to keep some buffers. Those buffers are usually first in, first out kind of buffers, that whatever data was written onto the bus first will be stored, and then that will be pushed on the bus later. That will be pushed on the bus first. The data that comes afterwards will only be pushed in the second cycle, and so on. So that is first in, first out. This is the queuing mechanism, which you would use in what do you say, clock synchronization across two different domains. So how big a FIFO would you need?
Sir, it can be application dependent.
Yes, it is largely application dependent. It depends on the kind of variation in frequency, like what are the two different frequencies that you are merging, and also on the how frequently are you expected to do this data transfer between two domains. If it so happens that you are transferring data in every cycle, then it can't really happen that we use a FIFO to take care of it. Because then if I'm sending 1 gigabytes of data from one part of the chip, and the other part of the chip can accept only 800 megabytes of data, then 200 megabytes of data we're ending up losing. So we understand that not every cycle would require data transfer, and therefore we can still operate two different parts of the chip at different frequencies. If we require it in such a way that data transfer rate has to be similar, then both parts should operate at the same frequency. Then a FIFO would not help. But a FIFO can help when there is a probability of empty cycles And in those empty cycles, the slower frequency system would pick up the data from the FIFO. Is this part clear? Hello? Are you able to, any questions on this? If you don't tell me, I will simply move forward. वो फिर अच्छा नहीं है ना?
और एक बार सर रिपीट कर दीजिए ना.
Okay, so let me see if I can use the whiteboard to explain it again. Whiteboard. Are you able to see my whiteboard?
Yes, sir. Yes, sir.
What we are saying is, let us say there is one system which is operating at 800 megahertz, and there is another system which is operating at, let us say, 1 gigahertz. And there is a bus that connects them. So at the interface of the bus, you will use what is we call as a FIFO. And the other side also you will have a FIFO, because those two are asynchronous domains. So there could be a time when this is operating at 1 gigahertz and this is operating at 800 megahertz. That kind of a thing also exists. So you have FIFO on both the sides. Now we understand that neither of the two systems would want to communicate to the other system at the full frequency F. Okay, they want to communicate at the required frequency F, but the activity factor or the number of cycles in which they will want to write is not 100%. Typically, this activity factor is of the order of 0.1, 0.2 at most. Okay, so you consider this probability factor, and then you say, okay, if this is the kind of data that I have to send from this port to that port, then since I'm transmitting at 1 gigahertz and an activity factor of 0.1, let us say, I will have 100 megahertz or 100 megabytes of data to be sent per second. On this side, the system is operating at 800 megahertz. So it will accept up to 800 megabytes of data per second. The system is matched. Now let us say the activity factor, is this thing clear? That if you're sending less data, just at a higher frequency, then you will still be able to transmit all the data, because the capacity of the accepting system is still much larger than the data being sent. Are you able to see this?
Yes, sir.
Yes, sir.
This part is clear. Now let us say the activity factor was 1. Now what happens? Or let us say 0.9. Now what happens? I am sending 900 megabytes of data per second. But this part of the system can only accept 800 megabytes of data per second. So what happens to 100 megabytes?
We'll lose it.
We will lose it. So this kind of an arrangement cannot work, which means that this system cannot operate at 800 megahertz. This system has to operate at 900 megahertz. So while FIFO could help when the capacity was matching across the two zones, if the capacity mismatch happens, then you have to change the frequency of operation of the slower system. Then the FIFO is insufficient. Are you able to see this?
Sir, you mean to say that if the receiver is having the higher frequency, we can give the input at a lower frequency also, right?
I'm sorry?
If the receiver is having a 1 gigahertz frequency, so if you want to give the data to that, so we can apply the data at lesser than that frequency. Yeah?
Yes. So now you're able to see the full picture. Is this clear? I was assuming that you were able to see my full whiteboard, but it was not the case. So is it better now?
Yes, sir.
Sir,
Any questions here?
Is this the same concept of synchronizer? Like
Yes.
We use some extra flip-flop to change, interact with the two different frequencies.
Yes. So over here we are saying we're not using a flip-flop because flip-flop is larger in area. We instead use a FIFO. It is denser. Okay.
So essentially, the receiver has to be at the operating at a frequency lesser or equal to the
Yes.
lesser.
So you have to always match the data rate, the data transfer rate. That's the baseline. That's what I wanted to emphasize by talking about in this detail. Is that okay?
So how do we overcome this challenge? I mean, we increase the frequency of the receiver's end, or we use something else, like we don't use FIFO or something else.
So you cannot do anything else. You have to change the frequency
to
be able to match it.
Yeah.
No other memory type or nothing else will be able to match it.
Okay. Okay.
Sir.
Yes, sir.
Sir, FIFO can only divide the frequency or can also multiply, because Raghav said it will give the frequency in subdivision. But in the second case, when you showed, it required some higher frequency. So can we use the FIFO for in the reverse order?
FIFO cannot generate data. Na? FIFO has a limited capacity. It can store only as many number of words in it. If the other side needs more data, then how do we do it? We can't do it. So Vaishnav is asking what is the exact internal structure of FIFO. So Vaishnav, do you know what the exact internal structure of an SRAM is? Not yet, huh? So we'll come into that. Don't worry. So that was about FIFO. Now what about last in first out? I've already given. You know, we use it whenever we want to implement stacks in our system. We use last in first out kind of a memory. So what is happening in these last in first out and first in first out is you do not really look for an address from the user. You maintain an internal pointer which addresses the locations that need to be addressed. For a FIFO, you have a read pointer and a write pointer and an output which you would call as an overflow output. So write pointer means I have to write in this location. A read pointer means I have to read from this location, and overflow means my the mismatch of 900 megabytes versus 800 megabytes that we were talking about is there. Therefore, there is a system failure. A LIFO also, you will have a read pointer and a write pointer, and the write pointer, the write pointer would be very close to read pointer at all times, because you're talking about last and first out. In FIFO, read pointer and write pointer can be far away, depending on the size of the FIFO. Shift registers, you know, what is a shift register?
So temporary data storage.
Yes, temporary data storage, just in the lines of what do you say, synchronizers, as Moin was telling about, that to synchronize between two clock domains, we use shift registers. Yeah, if it is about the same, so okay. When you were talking about these two clock domains, we said that the frequency is different, but there can be a case where I have two systems or two voltage islands, both operating at 1 gigahertz. Just that they are far away. From each other. So there would be latency between them. In such a case, what happens? If there is a latency between two domains, then all that you need to do is you need to use just one or two layers of data storage, depending on the latency size. In such a case, you use shift registers or flip-flops. Otherwise, you would, if there is a frequency difference also, then you necessarily need a FIFO to be put in place. Is that okay?
Overcome that latency. So to overcome that latency between these two voltage islands, we use shift registers.
Yeah, latency means that okay, I'm operating at 1 gigahertz, but to transfer data from one part of the chip to the other, I take 200 picoseconds. So when the clock edge comes on that side, my data is not yet ready there. So I need very small temporary storage, just 1 word or 2 words, and for that I use shift register.
To match up to that speed.
Yeah.
Okay.
Synchronizing. Okay. And then we come to the next part, which is content addressable memories. Who will tell me what a content addressable memory is?
Sir, in this we will search.
Search for the address, it will search for the content.
Content so we will search it out for the content and it will return the address.
So in content addressable memories, you give the content that you want to find. So you are saying, let us say there is a memory which stores names of all the students in this class. And someone wants to see that is there a student named Akash in the class or not? And then they may need additional information. What is Akash's roll number? Let us say. So we have the content available with us. We want to search at what location are details of Akash stored. The location at which those details are stored, I will then give out some data on that from that location. What would that data, output data be? That will be his roll number. So in that, what is happening is I am inside the memory doing the comparison, generating what is called as a match signal, and then giving the output considering that as the desired address. Are you able to see this? So this is content addressable memory. I do not have the address location which I want to read. I do not even know about it. But I know the content that I want to match. So I give that match content over there, and the location, all the locations for which this address will be matched, there will be a read operation that is initiated. Is that okay? Faisal, you have your hand raised.
So I just want to clarify a statement about shift register in FIFO. Like in shift register, due to latency, we are using shift registers.
So you could also use a FIFO there.
That's why I was confused, sir.
Yeah, you could also use a FIFO there. Shift registers are if you just need to have a few words, then shift registers are more area efficient than FIFOs. But if you need more number of words, then FIFOs are more area efficient.
So, like, what's the difference between FIFO and shift
area efficiency?
Okay. Okay.
FIFO is based on the SRAM kind of an architecture. Shift registers are based on flip-flops.
Okay, okay, sir. No, not as clear. Thank you.
Okay. So content addressable memories. Any questions about that?
So like in this, we are trying to go the reverse way from the content to the address. But like for the content matching also, there would be some kind of reading from a particular location that widget matches. Wouldn't it be like,
yeah,
like initially there would be some reading?
Yeah, we will. So in a typical SRAM cell, you have to have a separate, like if it was a typical SRAM, then you will have to read, you will have to compare and then say whether it's a match or not. So you will have to, if it's a 100 word RAM, you will have to do 100 cycles to do even one comparison. Am I right?
Yes, sir.
But in a CAM, what happens is every memory cell has a comparator in itself. There is comparison happening in every memory cell. So you just throw the data that you want to compare to the entire memory array, and whichever word there is a match, the memory array will highlight, oh, there's a match here.
Okay. So the operation when we throw the data and the cell picking up that data and comparing it, what is that operation called? It will be reading, writing?
That is called compare.
That is compare. Okay. That is separate kind of category itself.
Yeah.
Okay.
Okay.
So, okay.
And do you realize that if I have to do this kind of operation, it will be very high speed, obviously. And instead of 100 cycles, I could do that compare in one cycle only. But it is much more area penalty because now there is a comparator in every cell. And it is also much more power hungry because you're doing so many comparisons in parallel. So the peak power consumption is also very, very high.
Yes, sir. Yeah.
So overall throughput is very high, but those challenges also exist. So you're getting good on the axis of performance, but really sacrificing big things on power and area. CAMs are therefore used in very close association with processors. They're also called tightly coupled memories at times. They're very tightly coupled to processors, almost as a part of the processor. Very commonly used for lookup tables. And they're also used in routers, for example, communication domain routers, where you know that, okay, my destination is America. Now, which port to send my next data packet to? So I search for America and I identify which port America is programmed at, and so on. So that is content register memories. Again, non-random access. I do not give any address to the memory. I just give a content, and that content, the remaining information on that address, matched address, is given out to the user.
So just a small point. So like when we are throwing the data to the whole array kind of thing, so every location comparison is done parallelly, or at every location in the array.
Yes.
Okay, that's why the performance thing comes in, because everything is parallel. Okay,
yes.
Got it. So thank you.
Okay. Then all these were what we were discussing till now were volatile memories. What does volatile memory mean? That when you power off the system, the information would go away. It is volatile. But we need non-volatile memories also. That is what you have in your cell phone also. 128 gigabytes, 64 gigabytes of memory in your cell phones. So that non-volatile memory is a different range of memories altogether. And again, non-volatile memories are two types. One is non-volatile read-write memory, and another is read-only memory. We'll come to ROMs later, but where do you think non-volatile read-write memories are used? EPROMs, EEPROMs, flash, do you know what they are?
Hard-based solid-state drives.
The boot sequence.
Boot sequence.
Pen drives.
Pen drives. Okay, pen drives are what kind of memory?
Flash memories.
Pen drives are flash kind of memories. What are EPROMs and EEPROMs?
Electrically erasable.
Electrically programmable.
Electrically programmable ROM and electrically erasable and programmable ROM. So flash is actually a EEPROM only, a different kind, a different density. We will look at it in detail in the later part of the course. In the second half of the course, we will look at flashes and DRAMs. So we will see why flash is so much higher density than regular EEPROMs, for example. So how has the flash technology completely changed the way we use storage in advanced systems today? So EPROMs, electrically programmable ROM, where do you need it? Why do you need it?
So like someone mentioned the boot sequence, like once we store the instructions and they will automatically be read, and we don't have to write into this. We will just write the instructions once and then it's hardwired.
Yes. So EPROMs are usually used for instruction storage. In fact, if it so happens that you are very clear about what your boot sequence would be throughout the life cycle of the product, you will not even use an EPROM. EEPROM is less dense than a ROM. So you would instead use a mask programmed ROM. It is much denser. But typically we understand that system upgrade may happen, or tomorrow I may want to add some additional features into my chip, or enable a new set of features which are there in the debug mode today, but once we validate them on silicon, we will want to enable them. So the first few lots, the first few months, you give only the vanilla feature. You program the EEPROM in such a way that only the vanilla features are available. And 1 year down the line, when you have well tested the additional testable features or additional features you had on the chip, you offer them also to the customer by just changing the program on your EEPROM. So they're also used. And what is mass programmed ROM? Read-only memory, you understand. What is mass programmed?
So from the name, like it to me comes like that other kind of fabrication time only you are kind of like programming it like at the mass level itself, like you are directly at the you are like fabricating it such that you get that at that time chip fabrication itself. But I'm
Very
not
good.
sure.
Yeah. So is this point clear to everyone? When we are saying mass programmable or mass program, it means that at the time of designing the mask for that particular chip, I already decide what is the data that needs to be stored. So can you ever change the content of a mass programmed ROM?
No, sir.
No. But because it is mass programmed, we are already preempting what data needs to be written into the ROM there. It is much, much denser than EEPROMs and EEPROMs. And ROMs are again. So typically any die would have at most one ROM. So जहाँ पे हमने SRAMs की बात करी, that every die would have hundreds of SRAMs. Some would be like for register files. Another set would be for L1 cache. Another set would be for L2 cache, L3 cache, and so on. ROMs, typically the entire chip would have only one. That too only for the purpose of storing the boot code, which was pre-established before the system was even manufactured. And why do you think we need a programmable ROM?
Sir, in programmable ROM, some sections of the code memory is being stored, and if there is some over-the-air updates, so then this programmable ROM can be used.
So this is still a read-only memory. You can't change the contents. Programmable ROM means, for example, let us say there is some part of the system which is failing. You want to disable it, or you want to send little higher voltage to it so that it starts to work. Now, since this part is already failing, or you suspect that it would fail in the field, you already calibrate the system in such a way that this chip would generate a higher voltage than regular. These PROMs are fuse based, and they are typically used for calibrating the system so that it operates at an optimum, say, voltage or frequency or throughput.
So what exactly was the difference with the EEPROM and this PROM? I'm not able to get. Like,
okay, EEPROM is electrically programmable. You can apply a voltage of 12 volts to the chip and you can get it going. Fuse ROM may not be electrically programmable. Fuse ROM, you will actually have to physically blow away the fuse. Blow away the fuse means you will actually have to throw a laser at a particular place, generate the heat, and burn away the metal from there, so that the connection to VDD or to ground is removed. Something like that.
But both are used for the same purpose, functionality wise.
Yeah, but fuse programmed, you do fuse programming inside the fab itself. EEPROM you can do at the customer end.
Okay, so like in this mass program, other instructions that we need to be, for example, boot sequence, they are fabricated at the fab itself. Similar
Yes.
is for this PROM also.
No.
No. Okay.
PROM will not store instructions. PROM will only store calibration data.
What is that actually?
What does that mean? Suppose my chip is manufactured in slow lot. I now want to operate this particular chip or this entire lot at 1.14 volts instead of 1.1 volts, so that I get the required frequency. This is a one-time programmation that you will do at in the fab by blowing away some fuses. This is not about storing new set of instructions or a particular set of instructions. Is that okay?
So like after I have fabricated at a particular lot, then I'm doing kind of initial kind of fabrication step for this to make it operable.
After a fabrication has happened, I estimate what lot the device is at.
Yes, sir.
Now I simply fix that, okay, if it is a fast lot, then the leakage is going to be very high. So I have to lower down the voltage of operation so that leakage comes under control. Because it's already fast, performance is not an issue for me. So I will trim. I will say that, okay, instead of operating at 1.3 volts, operate the chip at 1.26 volts.
Okay, and this calibration will be done using this PROM.
Yes.
Okay, sir.
Clear for everyone? या खाली राघव को समझ में आया?
Yes, sir.
Any questions? Please feel free to ask.
So, and this last step of the PROM will be done and also in the fab itself.
Yes.
Okay, sir.
Hello.
Yes, Shivam.
Yeah, sir. I was able to understand like PROM is used for storing the synchronization information, as you told. Like if we have made a chip in fast load and we
Okay. So we do not make a chip in fast load. Chip gets manufactured in the fast load.
We categorize it. It is in
Yes.
fast load.
We identify that it is in the fast lot. Yes.
Sir, so how PROM is used there, like to store the information? Like we need to use it in like lower voltages.
Yeah. So what I will do is the voltage regulators on the chip, they always have some calibration bits.
Okay, sir.
I will make my logic in such a way that the information from the PROM goes and triggers those calibration bits in such a way that this voltage regulator now generates only 1.26 volts instead of 1.3 volts, or 1.14 volts instead of 1.1 volt.
Okay, sir.
Okay.
Yes, sir.
Similarly, let us say, because we are in the memory design course, let us say there is some location inside the memory that is failing. I can add some additional redundant memory in the overall chip and say that if this particular location is failing, if this failing location is addressed, then instead of reaching out to that failing location, go to this replacement location.
Yes, sir.
This again is programmed by using PROMs.
Yes, sir.
Okay.
Okay, sir. Thank you.
Yeah. Anything else? Great. So now whatever be all these kinds of memories, whether it is PROM or ROM or FIFO or SRAM or DRAM or flash, whatever it is, there is a structure to, yes, please. Yes.
So can I say that the PROM is storing the information of like which cell is working properly and how many extra cells are available to us, so that it can allocate in the future?
PROM will not do those evaluations itself. PROM will only store the location of the failing cell, for example. And the failing location, now there will be some logic on the chip which would say, okay, if this location is failing, let us redirect the addressing to that other location.
So there will be a controlling unit also in the memory section.
Oh, yes.
Can control this.
Oh, yes. We will look at the insides of the memory in just a little while. I was about to go there only, in fact. So, but before we go there, let's just have a quick look at, how SRAMs, DRAMs, and flash compare on various axes. So SRAMs are very, very fast. They have access times at times of the order of hundreds of picoseconds in advanced technologies. DRAMs are fast. Their access times is of the order of nanoseconds, tens of nanoseconds. Flash is much slower. If you want to access a flash, the access time is of the order of a few microseconds. So flash cannot really be used as a cache. For cache purposes, you need an SRAM only. L2 or L3 cache, you could think of DRAMs, but not flash there. There is another reason why flash cannot be used in L1 or L2 caches. Why? Because look at the third row, the parameter called endurance. Endurance means how many reads and writes can I do on this particular memory. For SRAMs and DRAMs, it's almost infinite. But for flash, it's of the order of, say, tens of thousands. Now, how does that limit flash from being used as a cache? Because if you can, for example, if you can do only 1 lakh writes onto a flash, you have a chip that is operating at 1 gigahertz and memory activity factor is 0.1. 1 gigahertz activity factor 0.1. How many accesses do you need to the memory within 1 second? Quickly.
0.1 giga.
100 million. Of this 100 million cycles per second, let us say only 10% were write cycles. So how many write cycles?
10 million.
10 million. How many times did we say a flash could read or write? Could you write into the flash?
1 lakh.
1 lakh. So in less than a second, the chip will be done. Are you able to see this? So even if I improve the speed of flash so that it matches the speed of the processor, due to endurance reasons, I cannot use flash as a cache. Flash, however, is a very, very good and dense means of data storage in the non-volatile space. Is that okay? Are you able to see this aspect?
Sir, how did this endurance decide for a memory which in better and?
Okay, so for now you can say that endurance is decided by some reason, but we know for flash that endurance is low. So if you would do the course of solid state devices and study about reliability mechanisms there, you will see that when a device is operated at a very high voltage, its reliability degrades very significantly. So you can use the device at a very high voltage only for a short duration of time. As we will see in the later part of the course, when we design flashes and when we do read and write in the flashes, we operate the memory at very high voltages, 12 volts, 15 volts, 18 volts. So the device degradation is very fast, and therefore flashes have low endurance. Is that okay? So then another thing is that DRAMs require refresh. DRAMs are dynamic random access memories. As we discussed just a little while back, DRAMs would store information on capacitors in form of charge. So capacitors would not be able to replenish any loss of charge due to leakage. And all devices leak. So after some time, the charge on the DRAM capacitor would kind of go so weak that you cannot read that DRAM capacitor. So what we do is we write into the DRAM capacitor at every predefined frequency. This write operation or this periodic write operation is called refresh. And that is the reason why DRAM also consumes more power than SRAMs and flash memories. Is that okay? We will go into much more detail of what refreshes and how it is done. But for now, just comparing these three types and arriving at a conclusion that I can use SRAMs for L1, L2 caches, DRAMs for L2, L3 caches, flash for final storage. Are you able to see this? This is where we started today's session from. Are you able to see the logic behind usage, the way we use them? Vishal?
So the L1 and L2 caches are volatile. Processor actually interact mostly with them. So isn't it a bad thing, like whenever the power is lost, this interaction miss rate will get high?
Yes, you lose that data.
Generally in some application, we store the instruction in processor itself. So those instructions will never erased, if I'm not
But
wrong.
if the power is lost, the processor goes off.
But again, when the power is on, like in the case of Arduino, if I program, if I remove the power supply and again connect it, it will hold the program which I had uploaded.
Okay. So what happens in such systems is that there would be some non-volatile memory also placed on the chip. So the power down sequence involves storing the present state of the processor onto that non-volatile memory, and the boot up operation involves recovering that information from the non-volatile memory and booting the system up in the desired manner.
Okay, so whenever the power is on, this booting will load this instruction in volatile memory.
Yes. Okay. Akash?
Sir, you mentioned that in the phone that we say 8 GB RAM or 16 GB RAM, we use a DRAM there. But sir, DRAM is basically slower than SRAM, and it also requires a periodic refresher. But still, we use DRAM. Is that it because SRAM consumes more area due to that trade-off?
Yes, it's DRAMs are much denser than SRAMs, and in memories, area is
gold, diamond.
Diamond.
Okay.
Harshit?
Sir, what does scalable mean?
We're just coming to that. So scalable means, so what is technology scaling? What is technology scaling?
Technology 65 nm, 7 nm.
Yeah, we are able to reduce the size of devices and still maintain the frequency of operation or get a better frequency of operation, better power and all that. That is what scaling meant, being able to reduce the size of devices. So while SRAMs is only transistors based, all transistors, so you can scale it. Flash, as we will see later, is also only transistors primarily. So you can scale that also to some extent. But DRAMs, we're talking about transistors and capacitors. So capacitors, if you reduce their area, what happens? The value of the capacitor reduces. So you can now store lesser charge onto the capacitor. So scalability goes for a toss, because lesser charge means I have to, so lesser charge means that the charge would become not readable much earlier than previous implementation, previous technology. So it means that the refresh frequency has to be increased. It means memory would not be accessible for all those refresh cycles, which means that overall throughput that I can expect from this particular memory would reduce. So that is why we are saying it is bad in terms of scalability. Does that help?
Yes, sir.
So if we are using like capacitors with lesser areas, why the frequency of refreshing is increasing?
Okay, so if the capacitor is of lesser area, what happens? The value of the capacitor
will decrease.
Reduces. The value of the capacitor reduces. Even if we say I keep the same voltage, what happens to the charge stored on the capacitor?
It will also decrease.
It will reduce. Now, Let us say the devices are also leaking exactly the same way as earlier technology. In fact, device leakage increases as you scale. Let us say it is the same as the earlier technology. Now what happens?
Now we will not able to read, like it will leak more.
It will leak more. So I will
yeah.
need to refresh faster.
Okay. Okay, sir. Yes. Sir.
Clear, everyone?
Yes, sir.
Yes, Nikhil?
Clear.
Okay.
In Flash, you said we use some high voltages because of its endurance is poor, but you are saying that the power is low.
Yeah, because you use other schemes so that even in the presence of that high voltage, the currents are low. Okay. Overall, you do lots of things in parallel when you go to that high voltage, and therefore you still need lesser power only. You will see. We'll come to the Flash implementation later. Okay. So yes, there's a question. Okay. So now, as I was mentioning, whether it is a flash or a FIFO or an SRAM or a DRAM, there is one structure, a common structure to the memories. All these memories. Memories are typically organized as arrays. So as many rows and as many columns. The number of rows and columns can be different. They could be the same. So on the row side, you need to have a decoder, address decoder, to select the desired row, desired location. And on the column side, you need to have what we call as an IO interface, which would receive data to be written and give out the data output. So IO circuits are required. In addition to that, to manage the aspect ratio of the memory, you will also have what is called as a column multiplexer. So typically, whichever memory you talk about, these three components would actually exist. In fact, there would be an additional component over here, which we can place it over here, which is called as control block. So all the control signals would come to this block. Whether I want to read or write, signals like clock, signals like let us say sleep, etc., would come to this control block. This control block is in those terms a kind of a brain for the memory. Okay. So when signals come to this control block sends out signals across the board to MUX, to the MUX block, to the IO block, to the decoders, so that they can operate in the desired manner. If it's a read cycle, the sense amplifiers and the IO would get activated. If it's a write cycle, the write driver would get activated. So the control block is kind of the mastermind of the memory. Everyone follows whatever the control block says. And in those terms, the control block in one way manages what we call as the state machine of the memory. You don't need to go into the details of the state machine. What I want to, my intent of sharing the state machine with you only is that memory could be in multiple states. It could be in idle state, simply waiting for the next clock cycle. It could be in pre-charge stage, getting ready for the next clock cycle. It could be in ready stage. Okay, I'm ready now. Give me the new address. It could be in read stage. Oh, I'm doing the read operation. It could be in write stage. I'm doing write operation. It could be in outputting stage where read operation has happened completely, but my output latches will now throw out the data. And it could be in standby state where we say that memory can't be accessed even if you give it a clock. It is in standby. It's not being used. And these are just few representative stages. There could be other states like test. There could be other states like sleep. There could be other states like scan. So all these different states of operation of the memory are controlled by the control block over here. Any questions?
So the different states in the memory would be, who will be deciding exactly where the control would be also be getting some kind of deciding that which state to memory have, but what will be the deciding factor, like which state you should go in?
You tell me.
So I mean, is it like the control will be like it will be like communicating with the processor, and
so the processor will give the signal whether I want to read some address location or not, is it not?
Yes, sir.
So that read signal is coming to the control block.
Okay, and then it is passing to the decoder or the IO, whatever the kind of operation.
It is masterminding. It is managing the entire show for the processor now.
So that like it is the interface between, we can say, the memory and the processor.
So if you want to call your brain as the interface between your body and the outside environment, yes, we can call it as an interface.
Okay. And sir, by the memory, do I call this the array the memory, or this whole decoder, this whole infrastructure as the memory?
So the entire thing is called a memory. The array is called memory array.
Okay, sir.
Sir, this is a bit, actually we are reading bit right here. Generally in the case, if you have the byte addressable memory, like if I am correlating it with the CA codes, we have MAR and MDR. I suppose the input of the decoder may be MAR register, and the output of this IO may be MDR. So yeah. MDR will be of 8-bit something size.
That depends. So okay, the processor that you're looking at, you're looking at it only in terms of how many bits. Memories could have, let us say, for example, if you also want to implement what is called as error correction codes. You have heard about error correction codes?
Yes, sir.
What are error correction codes?
We pass some code to check like where's the code. Like when we receive some signal, we check it. There is a signal or like with parity or something.
Yeah. So we encode any data and at the receiver end, and then we send it. And then at the receiver end, we decode it and we also do some validation checks. If there is an error, we will be able to tell that there was an error in the transmission, and some number of errors you will also be able to correct. So that is why it is called as error correction codes. So instead of storing, say, 32 bits, you would store 39 bits inside the memory and then apply ECC logic on it. Okay. So in CA, you talked about MDR and MAR, where addresses were also, let us say, 8 bits only, and data bus was also only 8 bits. But for an SRAM, if there are 100 or 1000 locations, how many address bits do you need to decode?
12, 10 or 9 or 10.
You will need 10 locations, 10 addresses. So what that means is that your system processor will send overall memory address in 2 cycles. That does not mean that your memory will have only 8 address bits. The processor has to send all the required bits. How it sends it, it is the protocol that the processor will set.
Got it.
I'm sorry?
Got it, sir. Understand.
Huh? So control in those terms is the brain of the memory. It tells what needs to be done. So like your brain tells your hand how it needs to move, how your leg needs to move, how your head needs to move, everything. In the same way, control kind of manages the entire, orchestrates the operation of the memory at all times.
Sir?
Yes, Raghav?
So just like you mentioned about the error correction code. So like one of the scheme is, for example, this is a Viterbi scheme also. But if I am moving towards a higher, more kind of error correction, then the number of states that I need to store also increases.
Yes.
So will I basically, the memory would be specifically designing for that more kind of accuracy, or like the same kind of array and it would be controlled by this control region depending on how it needs to control?
So if as a system designer, for example, you want to design a automotive chip, if as a system designer you say that I want Viterbi kind of decoding there, then you know that you will need this kind of storage space. So you order a larger memory, you place a larger memory there.
Okay. So my memory will also be like application specific, or the and that error correction will be in an application, like what how to apply it.
So there is some processor that wants error correction codes, another one doesn't want to waste area and time on it because the application is such, so they will not use it. They will use a smaller memory.
Okay, sir. Okay, got it, sir.
So memory will not do any magic. Memory is there just to store the information. If you have to store more bits because you want error correction, then you need a larger memory.
Bigger array and everything else bigger.
Yeah. Okay. So a complex state machine is what a memory would usually involve, and the signal flow inside the memory would look something like this. You have, as I said, address, clock, read, write, all those signals coming here. The clock generator would generate an internal clock. Pre-decoding addresses will generate an additional or internal set of addresses. They will go to a post decoder. They will generate what we call as a word line. Okay. The word line would select the memory cells in the entire row. So all these memory cells in this row would get selected. The memory cells will themselves discharge what we call as bit lines, BL. Okay. They will go to what we call as sense amplifiers. Sense amplifiers will be enabled through a control signal called, let us say, sense amplifier SA enable, and the output will be thrown out through the output buffers. I very quickly ran you through this signal flow. Who will now repeat it for me?
Sir, maybe I can do that.
Yeah, please.
So once whenever a read operation is required, the clock generator generates a clock signal along with also we'll have the address of the memory location, and this address and the clock are being fed to the decoder, which decodes the word line which has to be active, from which the particular word or a sequence of bits are selected. And once the word line is set high, then the bit lines are charged or discharged accordingly. And then these are available at the ends of the sense amplifier. And during this read operation, the sense amplifier enable is also set high. And the output of the sense amplifier determines which bit is read from the memory cell. And these are sent to the buffers.
Very good. Thank you, Ranjit. Is this clear to everyone? Anyone else wants to go through this flow again or has a question?
Two decoders. The pre-decoder will decode the address of CPU, like what address it gives, and the post decoder, what it exactly does.
Okay, so let us say I have 1000 words in the memory. To decode 10 bits, how big a NAND gate do you need? 10 input NAND gate? You've already done the DVD course. Do you want to generate a 10 input NAND gate?
10 size of NMOS?
Nahi hoga na? It will be very slow also, and it can fail. Such a long stack, you're operating at 1 volt only, and 10 NMOSs, each one of them will have some voltage drop across themselves. So how do you implement a 10 input NAND gate? We also saw that example in the previous course. How do you generate a large input AND gate or a NAND gate? You do it in stages. You say, okay, I will use 3 input NAND gates in the first stage. They will lead to some number of outputs, and I will use a 3 input NAND gate at the second stage also. something like that. So pre-decoding is the first stage of address decoding. Post-decoding is the second stage of address decoding. Combined pre-decode and post-decode would decode your 10 bits of address into one output.
So generally, SD card which we have in the phone will carry only the array part or the complete this architecture.
You tell me.
What comes to my mind is I think it should carry the all architecture, because I think if we just add the array, then we need to have the IO ports and all also in the phone.
Yeah. So you have in terms of SDRAM or something, you will see there are only 8 data bits that are available on the chip. So, but your DRAM array would have how many columns? Thousands of columns. How will you access? So you have to have all these control circuitry, everything in there. That is what a memory is. Otherwise, you would call it a memory array.
Sir, the clock is first. The clock is at the very first time is fed directly into this post decoder, right?
Clock is fed directly to the.
Sir, the clock signal is only fed into this post decoder. I just wanted to
Into the
ask.
clock generator.
Okay, and the clock generator then feeds the clock into the post decoder.
Yeah, it would generate some other internal clocks. One of the internal clock goes to the post decoder.
So is the clock only going to the post decoder? So my question was this.
No.
Okay.
This is a super simplified representation for the first glimpse of operation inside the memory.
Okay, and so like after the sense amplifier, you have user output buffer. So what exactly it is offering here, the output buffer?
So a sense amplifier would say generate some output, 0 or 1.
Sure.
But the output may actually see a load of 200 picofarads.
Okay, okay, got it.
If you want to drive that big a load, you need some buffer.
Okay, okay, sir. Got it, sir.
Buffer is just a buffer.
Okay, fine. And so the latch here, this latch after the sense amplifier.
Yeah, we will see.
Okay, sir. Okay.
Just know that there is a latch. The purpose of it we will see later.
Okay, sir. And so just one more thing, like when we have enabled the whole word line, so for example, we have to read from a particular cell location. So we do the read from a bit line, for example, as you said. So before before that reading operation start, we will also enable that sense enable signal, like only when then.
Before or after we will see later.
Okay, sir.
Just know there is a enable signal that comes. Okay. So let there be some suspense. We are in the first class. Yes, Faisal.
So can't we just say the pre-decoder is deciding whether to read or write since it is in the control block?
No.
So both the pre-decoder and post-decoder are deciding the bit line, which bit line we should read, in which we should read or write.
No.
Then I am confused.
Pre-decoder and post-decoder are deciding which word line to select.
Okay. Yeah.
Okay.
Yes, sir.
So after like post decoder and pre decoder decides which word line to select, then how do we come at the bit line exactly? That which bit line to be selected in that particular word line?
Okay. So if you noticed in the one of the previous slides, I said there is something called a column mux in the IO.
Yes, sir. Yes, sir.
That is also, a column mux is also a kind of a decoder or a encoder, right? So we'll use that to select the bit line.
Okay, sir.
So again, as I said, this is not the memory. This is a super simplified representation of a memory just to give you a quick glimpse of what happens there. But I'm so happy that all these questions are coming. It means yahan tak sab samajh mein aa raha hai.
Sir, I want to add one thing, like it may be correct or wrong. What comes to my mind is 32-bit register, 64-bit register. We have PC, right? So if we add this address bases, so the rows will increase, the columns will not increase. So by this, the SA, the sense amplifier will not increase. So I think it is advantage for that reason we are moving for higher addresses.
Okay, now we will see. We will talk about it in the next class. Abhi time khatam ho raha hai. We will talk about this, how the increase in addressing results in change in the size of the memory array. We will look at it in the next class. Okay.
Hello, sir.
So remind me also that we have to. I will anyway pick it up. That is scheduled for the next class. But if I don't go in the required detail, you can remind me. Yes, Deeptanu.
हाँ सर, वो आपने तो उतना तक बोला है कि मतलब एड्रेस से व्हाट लाइन सिलेक्ट होता है, इसके बाद आपने बोला है कि कॉलम मास्क यूज करके हम बिट लाइन सिलेक्ट करते हैं, तो इसके बाद क्या है सर? एक
उसके बाद सेंस एम्पलीफायर।
नहीं वो तो मालूम है, लेकिन बिट लाइन में क्या मतलब? रंजित भी बोल रहे थे कि ये चार्ज कुछ तो डिस्चार्ज होता है, वो बात समझ में नहीं आया।
हाँ, वो आएगी. Don't worry. When we will come to the memory cell in the next class, we will talk about what happens on the bit lines when the read operation is happening. We will discharge the bit lines. And that differential in charge, one of the bit lines will discharge, the other one would remain at VDD. This differential we would amplify in the sense amplifier. We'll come to that. Don't worry.
Okay, sir.
But I'm happy that these questions are coming. That was the intent of taking you through this animation. The purpose is solved. Okay, so this was a semblance of read operation. If you want to do a write, again, it is something similar. You will use the clock generation, you will use pre-decoding, post-decoding, you will generate the word line. But now, instead of the sense amplifier, you have what you call as a write buffer, write driver. And this write driver makes one of the bit line to 0, the other bit line to 1. And when the word line is selected, I am able to write information inside the memory cell. Okay, so this word line selection path remains exactly the same, but for the write operation, because the data is coming from outside, this path gets enabled. Okay, and as we were talking about, they were asking about how many clocks are there and is clock only going to the post decoder. You see, I'm talking about a write clock over here. I'm showing it as coming from here, but actually it is the clock generation circuitry that sends the write clock. Okay. Any questions?
So in a memory where which is able to read and write, perform both the operations, so we use sense amplifier and this write buffer simultaneously.
Not simultaneously. We have both of them placed next to each other. We use them based on what operation is required.
Yes, sir. Yes, sir.
So not simultaneously.
Yes, sir.
Okay.
So for every bit line, do we have to have? So for every bit line, do we need a write buffer and a sense amplifier, or like only two for all the bit lines? It will split accordingly.
Yeah, when we will talk about this aspect ratio and the concept of column mux in the next class, and later when we will talk about IO design, that is when we will see how to, what is the, like you may have them on every bit line, or you may not have them on every bit line. You may have them on a cluster of bit lines. So that we will, that is a design flexibility that we have with us.
Yes. Okay.
Okay. And as designers, that is the freedom that you should exercise later. Talha, you had a question?
Yes, sir. I had a question. So in the writing operation, there are two parts, like write buffer and the pre-decoder also has an input, sir. So what, sir, we are this writing operation, where does the information go, from the D part or?
So just like the read operation also had two parts. There was a row decoder and a word line generation circuit. And there was an output determination circuit, which is called the sense amplifier. Over here, there is a row decoder and word line generation circuit. And there is a input conditioning circuit which is called write driver, which helps to write inside the memory cell. Similar hai.
No, sir. My question is that what goes means the information which you are writing goes through the write buffer or through the pre-decoder side.
You tell me, where is the D pin shown?
Yeah, it will go from the read buffer side. And what will go the pre-decoder?
The pre-decoders, the address decoding will get the address.
Okay. Address where to write. Okay.
You're writing on one particular address, na? So
Yes.
that address will go to the pre-decoders and the post-decoders.
Okay.
ठीक है?
Sir, in IO we have muxes, right? So in the read operation, I assume it as n is to 1. Now it's reverse, 1 is to n type of mux.
Yeah. So this would be a mux demux. So you have to have encoding and decoding both implemented in the IO region. Is that okay?
Yes, sir.
Yeah. So we will stop here. We will pick up from here in the next class. Any further questions? So in the next class, when we come, we will look at the signal flow in, say, the write cycle. As to over here, we just looked at this is the way, a graphical way of the signal flow. Now we will look at more timing diagram kind of a way of signal flow in the next class. And we will go into optimizations, and we will also have a look at the data sheet of the memory in the next class. Okay. So all the best, friends. See you on Tuesday. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.